Good afternoon, everyone. I'm Andrew Shumway. I'm a graduate researcher at the University of Washington. I'm working there with Professor Jonathan Toner, studying the formation and stability of brines as they exist on the surface of Mars. I'm here today to present some results from some experimental work that we've done looking at how brines may exist under more extreme conditions than previously thought possible. In fact, my results likely indicate that under certain conditions, brines may exist throughout the entire year and in the most extreme conditions on Mars, making them effectively unfreezable. So transient or perpetually liquid water on the surface of Mars, even in relatively small quantities, it has deep astrobiological significance. Water is the cornerstone in our search for habitable environments beyond Earth. And there are many hazards on Mars that potential organisms would face, including low temperature, low pressures, high exposure to radiation. But I think perhaps none are as difficult to overcome as the lack of water. So life on Earth can thrive in some of these most extreme environments, but all life as we know it needs water to survive. So if there are microorganisms on Mars, we should be able to identify their source of water. And even if there are no microorganisms alive on Mars today, soon we will be bringing our own life to the planet. Humans, and for potential future missions, manned missions to Mars, humans are going to require water, and likely the first missions will bring their own water. But this is inefficient because water is very heavy and expensive to transport. So it would be much more sustainable to find a source of water there on Mars that we could use. So for these reasons, characterizing water on Mars is critical in defining both present and future habitability of the planet, and it's central to our mission as astrobiologists. This presents a challenge, though, because when we look at the surface of Mars today, we find a very cold and dry place. It's not an ideal environment for life to exist. And while there's past evidence that liquid water existed, the water that is there, or that water is long gone. If we look at the phase diagram of water and the range of Martian surface conditions, we can see that any pure H2O would exist only as a solid, ice, or as a water vapor gas. But the surface of Mars is rich in salts, which reduces the evaporation rate and can allow water to exist under these extreme conditions. So a great deal of work has already been done to characterize Martian brines like these. Brines made from Mars salts can have extremely low freezing points, down to negative 74 degrees Celsius in the case of calcium perchlorate. Another way that water is predicted to exist on Mars is as adsorbed brines, or as adsorbed water. What's happening here is that water vapor will adhere to surfaces, in this case soil. This adhesion is just driven by van der Waals forces, which are weak electromagnetic interactions. But neither of these previously studied systems tells the whole story. Realistically, any brines that likely exist on Mars are within the soil. So it's essential to understand the properties of soil-brine mixtures, soil and salt and water. What distinguishes our experiment from these previously studied systems is that we investigate samples of soil and brine and find that they do not behave identically to either of these previously studied systems. So the goal in this experiment is to answer the question, under what conditions can brines exist in Martian soils? This comes in two steps. The first is to study how brines form in the soil by taking up water from the atmosphere. And we did this by measuring the water activity. If you are not familiar with water activity, essentially it is a measure of the effective concentration of water, or how much water is available for chemical and biological interactions. Next, we looked at brine stability to identify phase transitions such as freezing, salt precipitation, and glass formation in soil-brine mixtures. This phase diagram shows the phases for pure magnesium perchlorate brine as a function of concentration and temperature. And we find that soils cause brines to deviate strongly from this picture. In order to investigate these two themes, we created soil brine samples that are analogous to what we expect to find on Mars. So we've never had a return mission from Mars, so we don't have any real Mars soil to work with. So we have the next best thing, Mars soil simulant, which is essentially just crushed weathered basalt that mimics the composition of Martian soil. And for our salt, we chose magnesium perchlorate. We chose this because the wet chemistry experiments on the Phoenix lander found approximately 0.6 weight percent perchlorate in Martian soil at its landing site. So when you put it all together, you get a soil brine sample that looks something like this. And using these soil brine mixtures, our first task was to measure the water activity as a function of brine salt concentration. The way that we did this is we have our soil brine sample of an unknown water activity, and we introduce it to a reference material for which the water activity is known. Both of these materials are put into an evacuated chamber and held at a constant temperature, and water vapor is able to exchange between the two samples until equilibrium is reached. At that point, we can compare the mass before and after equilibration and calculate the water activity. So the water activities for both of the materials would be identical. So calculating the water activity and the brine concentration. So here are the results from that. But first, actually, I want to show you, this is what for the pure magnesium perchlorate solution would look like for water activity as a function of salt concentration. You can see that water activity is lower at higher salt concentrations. This is because at these higher concentrations, more of the water is interacting with the salt, so less of it is available to be used in other processes. Here in black are the data for a mixture of Martian soil simulant and magnesium perchlorate brine. The concentration of salt in this experiment was 1 weight percent. That's because it's very similar to the what was detected by the Phoenix lander. We also studied soil brine mixtures at higher salt concentrations. So you can see here in orange is 2 weight percent, and in red, 5 weight percent. And as we get higher and higher concentrations, it approaches the trend for the pure brine. So this has really big implications for the way that we study Mars-relevant brines. The lower water activity means that brines absorbed onto soil are less available to chemical and biological processes. Further, to address the question of stability and when these brines actually remain liquid, this drop in water activity should correspond to depressed freezing point temperatures, meaning that the brines will be more stable than previously thought. And we can confirm this by measuring the phase transitions directly using a differential scanning calorimeter. DSC what it does is it identifies phase transitions by measuring the heat flow through a sample as temperature changes. Anytime that a phase transition occurs, there will be a characteristic absorption or release of heat, and the DSC measures those changes. So here's the heat flow through one sample of 1 weight percent soil brine mixture at an activity of 0.91. The sample was cooled down to negative 150 degrees Celsius, and this plot shows you the change in heat as we slowly warm it up towards 0. At this point here, the heat flow drops suddenly. Melting ice is an endothermic process, meaning that it absorbs heat, and that's exactly what we're seeing here. We see similar features at lower water activities, 0.8, 0.73, but when we get to really, really low water activities below 0.5, this feature disappears entirely. It doesn't appear, so what this says is that water never freezes in these samples, even though we lowered the temperature to negative 150 degrees Celsius. So let's go back to this figure, which compares a pure brine with a 1 weight percent magnesium perchlorate brine soil mixture. Like I mentioned before, this decrease in water activity caused by the soil does in fact correspond to a decrease in freezing temperature. The depression of the freezing point is so strong that in samples below 0.5 water activity, the brines never freeze. And this is what we deem unfreezable water. Because in these dry Martian conditions, such brines will remain liquid over the full range of Mars's temperatures. As I wrap up, I'd like to leave you with just a few closing thoughts. Brines on Mars will likely exist as adsorbed phases onto soil, and they will remain liquid at much lower temperatures than pure brines. This expands the range of conditions where liquid water is stable and allows it to be available in some of the most extreme conditions on the planet. Adsorbed brines could serve as a potential source of water for microbes on Mars, but it would be an extremely hostile environment because of these very, very low water activities that we're measuring. And so this project has only just scratched the surface of this. There's plenty of more future work to do, many more salts to investigate, many different types of soils that we can use, clays as well. So that's the direction that I'd like to go in the future with this project. But to wrap up, I'd just like to thank my sponsors and my home department And I'll take any questions.
Yeah, we have time for a few questions.
Hi, Germán Martinez from the University of Michigan. Very interesting presentation. Thank you very much for that. I was wondering about the Mars analog soil that you used. Where did you get it from exactly, or do you have details on that one?
Yes, you can actually buy it online. It's at it is Mars Mojave Simulant, I believe is the name of the soil. It's Martian Gardens is
So
the
it's
name
the
of the company.
Mojave. Okay.
Yeah, yes.
Thank you very much.
Alex Palov, NASA Goddard. So when you did this experiment, when you put both soil perchlorate and another solution with known activity together, how big are those samples whenever you put what you're trying to equilibrate?
So the soil sample is about 0.5 gram,
Okay.
so they're pretty small.
Okay. Because concern was, whenever I do experiments with perchlorates, is that you can form like a crust, whenever particularly low pressure, so it can be deceptive. But at 0.5 gram, it's probably not the effect.
Mhm.
Right.
Jennifer Hanley, Lowell Observatory. Can you explain again how you determine the activity of water in your soil plus salt plus water one, and got it from the water plus salt one? Can you just explain, like maybe go back to that slide and explain it again, please?
Sure. I don't want to go too far back, but there's an equation to calculate it. So we weighed the sample before equilibration and after equilibration, so we can know precisely how much water is in each sample. And from that amount of water, you can back out the brine concentration and use that to calculate water activity.
So how's the water getting in there? Are you
It's exchanged through water vapor.
Okay, so it is. Okay.
David Stillman Swery. Similar kind of question. How much water do you have in this 1 weight percent sample? Like, did you start with a known amount, or because, are you daily questing it in and then waiting and then making the water activity measurement?
Sure. So we start with perfectly dry soil. We dehydrate it and treat it with a magnesium solution, and then we pipette in magnesium perchlorate brine, and then allow it to equilibrate at a water activity. Yeah.
Okay. Thanks.
All right, and I have one or two, and I'm going to pile on top of that. But and I get your process, but it's all based on a mass balance. Have you taken into account absorption? Because if you start from a perfectly dry soil, you're going to probably absorb a significant amount of water, and you have only 1 weight percent of perchlorate, so it's really small. So if you want to make sure that you really estimate properly the amount of water that goes in the liquid phase of the perchlorate, you need to make the same mass balance on the dry soil without perchlorate.
Right. Yes, we have done that. I just did not include the results in this presentation. But yeah, we did the same experiment without perchlorates, just a soil sample to see the effect of absorption without salts. Mm-hmm.
Do we have any other question? No.
Did those freeze? If it was just absorbed water? Because I would expect it wouldn't freeze.
We did not put those through the DSC.
Okay.
Yeah. So we didn't measure the phase transitions, but that's a very good, interesting thing that we should do in the future.
All right, so let's thank again our speakers for the morning.